Example, figure A shows a homogeneous rigid block weighing 12 kips or 12 kilopounds that is supported by three symmetrically placed rods. The lower ends of the rods were at the same level before the block was attached. Determine the stress in each rod after the block is attached and the temperature of all bars increases by 100 degrees Fahrenheit. Use the following data. So we are to solve for the stresses after both the block is attached and after also the temperature is increased by 100 degrees Celsius. So first we write our given, which is 12 kips for the weight of the block, and then the temperature change, which is 100 degrees Fahrenheit. We then write what is required, which is the stress in each rod. And this stress, as mentioned before, is the stress after the block is attached and after the temperature was increased to 100 degrees Fahrenheit. Oh, sorry, not increased to, but rather increased by 100 degrees Fahrenheit. We write our solution. Just like what was provided in the lecture video, it is always best to make some sketches, draw free body diagrams because it will really help in solving these kinds of problem. So let's say we make a cut there. So let's say we made this cut. Now what we can do after making the cut, we can exaggerate the possible elongations our material will have once temperature is increased and once the block is also applied. Now, like I said, just like in the lecture video, the purpose of the first step after doing some sketches is to have our material exhibit as if it has a free end. So what we do have here is it is as if we cut our rods and then we let our rod freely elongate due to temperature change. Okay, so just making some subscripts. The two rods at the side is the bars, steel bars, and the rod at the middle is a bronze bar. As stated in the text, the illustration here, our assumed thermal elongation of our bars has different lengths. For our steel here, at the same level of course, but the projected thermal elongation of our bronze is much higher as compared to our steel rods. Simply because, if you can notice in the given above, bronze has a much higher thermal has a much higher coefficient of thermal expansion. So basically, if both rods are subjected to the same temperature change, since bronze has a much higher coefficient of thermal expansion, as if you can notice the formula for strain, which is equal to alpha times change in temperature. So basically, the strain in our bronze will exhibit a much higher strain as compared to our steel, simply because it has a much higher coefficient of thermal expansion. Now, of course, if you can notice also, that is our assumption for the temperature change, the thermal expansion. However, if you can notice, although it has different projected thermal elongation, but once the block is applied, meaning we will now be considering the elongation due to the applied load, still our three bars will exhibit the same downward movement, okay, the same level, right? Because if we can notice in our illustration above, the bar is supported evenly by our two steel rods and our bronze rod. So therefore, this is now our compatibility equation, that the total elongation of our steel bar, both in terms of the thermal elongation and the elongation due to the applied load by the weight 12 kilopounds, is equal to the total elongation of our bronze rod. Now, substituting Hooke's law, of course, our thermal elongation is alpha times change in T times our original length, or you can always rearrange it to follow ALAT. Alpha times L times change in T. And of course, our elongation due to the applied load can be either stress L over E or PL over AE. Next, we can now substitute the values corresponding to each variable. Okay, substitute the values. For our coefficient of thermal expansion for steel, that's 6.5 times 10 to the negative 6 per degrees Fahrenheit. Oh yeah, by the way, I forgot to write the change in temperature, which is 100 degrees Fahrenheit, times the change in temperature, which is degrees Fahrenheit, times the length of our steel rod, which is 2 feet. Okay, we have to multiply our 2 feet by 12. That is in order for us to change the units, to convert the units from feet to inches. because of course if you can notice, our E, which is our modulus of elasticity, is in psi. As stated in our previous discussions, it is always best to anchor or to base our units to our modulus of elasticity so that it will be much easier to cancel later on. Next, we substitute our values for our thermal elongation due to the applied load. Still, our length is 2 feet. We multiply that by 12 inches in 1 foot divided by 0.75 inches squared for the area, and 29 times 10 to the power of 6 psi for our modulus of elasticity. That is equal to the terms from our bronze rod. Coefficient of thermal expansion for bronze is 10 times 10 to the negative 6. Now, if you can notice, again, I would like to reiterate the projected possible thermal elongation of our bronze rod due to temperature, and the projected elongation of our steel rod due to temperature is much higher as compared to our steel rod, simply because of the fact that our bronze rod has a much higher coefficient of thermal expansion as compared to our steel rod, which has only 6.5. Then the length of our bronze is 3 times 12, again, divided by 1.5 inches squared times the modulus of elasticity of our bronze rod. Now we do now, I refer to you to our calculator on the left. We substitute our values. So that's 6.5 times 10 to the negative 6. Multiplied that by 10 times the length. No, not 10, but rather 100, because that is the temperature change, times 2 feet times 12, which is the conversion of feet to inches. We'll get 0.0156. Now we do the term for our PL over AE. 2 times 12 over 0.75 times 29 times 10 to the power of 6, which you can notice has a lot of zeros. That is why it will be written here in the video that it is always best to eliminate the times 10 to the negative 6 in the denominator. What I mean when I say, since the value for constants of the load PST and PBR is the same, that's what I meant. We can always multiply the entire equation by 10 to the power of 6. So let me just erase that and multiply everything. The entire equation, both the left and the right side of the equation, by 10 to the power of 6. Of course, so what happens now is, for our PL over AE, the 10 to the power of 6 from our modulus of elasticity E will be eliminated. So to minimize the number of zeros after the decimal point. Now going back to our thermal elongation term, instead of 0.156, we are now given 15,600. It is much easier to deal with bigger whole numbers rather than a very small decimal number. Okay, so we have 2 times 12 divided by 0.75 times 29 times 10 to the power of 6. And of course, times 10 to the power of 6, we are given this value. Okay, we move on now to the bronze term. 10 times 10 to the power of negative 6 times 100 times 3 times 12 times 10 to the power of 6 will give us 36,000. Now doing the PL over AE term from our bronze. So 3 times 12 divided by 1.5 times 12 times 10 to the power of 6, which is, of course, since we multiplied that by 10 to the power of 6, I put there 3 times 12 divided by 1.5 times 12 only. That will give us 2. Then we rearrange the term. So that's 1.10344827586 P sub ST minus 2 PBR So let me just transfer that. Is equal to 36,000 minus 15,600, which gives us 20,400. Now, if you can notice, the number of decimal places after the decimal point for my example has way more numbers as compared to your calculators. It's simply because I am using an online calculator, an app. So for your case, you can always have it truncated to as to how many decimal places your calculator may provide. So next, we do our equilibrium equation, right? If you can remember the general rule in solving a statically indeterminate problem, which thermal stresses fall under to, is first we do compatibility and then we do Hooke's law and then equilibrium equation. Now, of course, if you can notice from our illustration above, that we have two steel rods and one bronze rod, and of course the weight of our block, which is 12 kips, it is applied at the middle of our block. So we do equilibrium equation. Summation of forces y is equal to 0, assuming going up positive. So this should be 2 p sub st plus 1 pbr minus 12,000 pounds is equal to 0. Okay, solve for PBR, but nevertheless, you can always do the opposite. If you want to solve first P sub ST, then you can go for it. Still, provided that what you did is correct, you will still end up with the same answer. But for my case, I opted to do PBR first. So PBR from our equilibrium equation is equal to 1,200. No, it's 12,000 minus 2 PST. And then we will be substituting this equation, second equation, into our first equation. So I'm just copying our first equation. Now we can substitute the value of our PBR, which is 12,000 minus 2 PST. So again, let me just transfer that because again, mathematics is just like English. It has its own syntax. It has its own grammar. It has its own structure. And the general rule is if you're solving mathematical equations or mathematical problems, you always align your equal sign. So that is what I just did. Now we solve. We do the parenthesis first. So that's 2 negative 2 times 12,000, that's a negative 24,000, plus negative 2 times negative 2 PST, so that's positive 4 PST. And we do add our 4 PST and 1.10344. It will lead us to 5.10344 P sub ST, which is equal to 20,400 plus 24,000. That will give us 44,400. That is 400, not 44 4,000. That's 44,400. Yes, I am making now the correction. Okay, so we divide 44,400 by 5.10344827586. Please refer to the calculator on the left. And that will give us 8,700. Now, if you can notice that after the decimal point, it has 1, 2, 3, 8 zeros before another 353, right? Now, that is that is the reason why it is always best to copy everything that is available in your calculator to avoid numerical discrepancy along the way, right? It's because if you at the start of your calculation, if you have truncated your values after the fourth decimal place, tendency is you will not get 8,700 with 000 with 8 zeros after the decimal point, because again that can lead to numerical discrepancy. That is why it is always encouraged to copy everything that is available in your calculator, especially if you're still at the middle part of your solution. So yeah, if you can notice, 8,700 exact. Then after calculating our P sub ST, which is 8,700, we can now substitute that value into our second equation, which is P sub BR is equal to 12,000 minus 2 PST. If we do substitute, we will be given positive 5,400. Oh, sorry, that's negative 5,400 because what I did in the calculator, it's the opposite. Now we can now solve for the stresses. Simply dividing the calculated piece by the areas corresponding to that rod. So for steel, that which has a value of 8,700 pounds, you divide that by 0.75 inches squared. We are given 11,600 psi, which is in tension. And of course, don't forget to box your final answers. Next, we can now calculate for the stress in our bronze. Still P over A. But our P here is negative 5,400. We divide that by 1.5. That's negative 3,600 psi. And of course, we can always rewrite that by accounting for the true direction, or the two, not yeah, which is 3,600 psi compression.